This is the video for pre-lecture 5. In lecture 5, we're going to be discussing Euler's method. And Euler's method is an approach that uses mapping to solve an ODE, in particular an initial value problem. So given an ODE like dx dt equals some function of x and mu with an initial condition x at t equals 0 equal to x naught, we want to try to solve for x as a function of time that satisfies the initial conditions. To do this, we're going to perform a time marching scheme, which sort of moves from one moment in time to the next, that will give the solution at discrete times. So for instance, that's going to correspond to x at t equals 0, obviously will be your initial condition. And we're going to use that to map forward to x at time delta t, which will be our first value after performing one map using the input information at x naught. We'll use that to map forward to our next time step, x at 2 delta t, and continue this on, so on and so forth, for x of n delta t. Notice that we don't have information at intermediate time values. We could maybe approximate that given the neighboring ones, but this is the idea of a discrete time solution, giving us information at just those delta t time intervals. We assume that delta t is small, so that this isn't really an issue, and the smaller delta t, generally the more accurate the solution is going to be, but it's going to require us to take more time steps to advance a certain amount of time. So the method for Euler's approach is based on the Taylor expansion. So the Taylor expansion says that if I want to approximate the value at x at time t plus delta t, given information at time x at t, I'm going to add to it delta t times dx dt plus 1/2 delta t squared d squared x dt squared plus 1/6 delta t cubed d cubed x dt cubed plus many other terms. In fact, we would refer to, in this case, all the terms of order delta t or greater as higher order terms. So what do I mean when I'm referring to a particular order term? So I would call this term, for instance, my order delta t squared term. Well, underlying that is an assumption that 1/2 is a value not too far away from 1, and that d squared x dt squared would also be a value not too far away from 1. So the magnitude of this term is really set by delta t squared. And again, we're assuming that delta t is small, something like 0.01 or 0.001. And by squaring that value, which is already small, it becomes even smaller, and so that sets the scale of the entire term. And so the order of a term corresponds to the exponent of the delta t component of that term. So if we neglect these higher order terms, we could make the approximation then that x at time index n plus 1, which we'll say is equal to our x of t plus delta t, is equal to x sub n, which is our x at t, plus delta t times dx dt. And so this is our map that we'll use to advance forward in time implementing the Euler's equation approach. And we can see this graphically. So if we assume that this is our value, x1, this is our slope, so this is our dx dt value, this is our time index delta t, then we can see that our new term x2 is just equal to x1 plus delta t times whatever our slope is, dx dt. And we can take another step starting at x2 to get to x3. Now, what you'll notice is that obviously the values are starting to diverge away from the analytic solution. But if we were to take smaller time steps, we would expect to be a little bit more accurate or more faithfully representing the analytic solution. So let's do a very brief example building off of that. So our function is very simple. Dx dt is equal to x, where our initial condition x at t equals 0 is equal to 1. And we're going to take steps of delta t equals to 1/4. So for reference, it's valuable for us to know what the analytic solution for this particular problem is. And so it can be shown that if we say, okay, well, dx dt is equal to x, I can use the method called the separation of variables to say, okay, well, that's the equivalent of dx over x is equal to dt. And I can take the integral of both sides. That'll give me log x plus, or sorry, is equal to t plus c, where that's our integration constant. I can rearrange this and say that that gives me x is equal to c1 e to the t, and implement my initial condition at t equals 0. E to the t is e to the 0 is equal to 1. So then c1 has to be equal to our x value at t equals 0. And so that's going to just give us x is equal to 1 times e to the t is our analytic solution. Okay, now let's approach this problem from the explicit Euler. And so what's the explicit Euler equation for this? So that would be xn plus 1 is equal to x sub n plus delta t times dx dt, which in our case, we're going to just simply say is equal to x. And so we're going to plug in here now the x value. The question then becomes, well, which x value do I take? Do I take the x sub n value or the x sub n plus 1 value? And for the explicit equation, which we're going to be using first, we're going to just simply assume that our dx dt is evaluated at time index n. So this will just be x sub n. And so that could then simplify to 1 plus delta t times x sub n, if we want to maybe make things a little bit easier. So if we're taking time steps of 1/4, that's going to correspond to 1 plus 1/4 times our x sub n value, which is just 1, and so that's going to give us a value of 5/4. Take another time step. X2 is equal to 5/4. Our explicit Euler is going to still just be 1 plus 1/4 times 5/4 now, and that'll give us a value of 25/16. Take another step would give us a value of 125/64, and this would be our value, at t equals to 1/4. This will be our value at t equals to 1/2, t equals to 3/4. And then finally, if we take one more step at t equals to 1, this would be what, 625 over 256, which is a value of approximately equal to 2.5625. Analytically, e to the 1 is equal to 2.718. So not too far off, on the order of maybe 8–9% or so. And if we were to take smaller time steps, it would give us a more accurate solution. Well, what if we're trying to solve a higher order ordinary differential equation? And so in this case, we're going to take a look at the Blasius equation, although we're not going to use the Blasius equation or boundary conditions, we're going to use initial conditions. We'd have to rearrange our equation, and so we could say something like, okay, f prime is equal to g, g prime is equal to h, and we can take these two values, substitute them in. So this g could go in for this f prime, and then our final equation would be h prime, which would be our third derivative. And so then we could say that h prime is equal to minus 1/2 g times f. So we have a system of 3 first-order ODEs that we have to go about solving. And so we can still use the Euler's method to do this, but we have to solve for all 3 of these simultaneously. So we have to create an explicit Euler equation for each of the 3. So we would say, okay, well, I can say fn plus 1 is equal to f of n plus delta t times df dt, which in this case is just g. Then I have my gn plus 1 is equal to gn plus delta t times my dg dt, which is going to just be h of n. And then finally I'll have h of n plus 1 is equal to h of n plus delta t times my h prime, or my dh dt, which in this case is going to be minus 1/2 g of n times f of n. And so you'll notice that effectively what I'm doing here is I'm taking the right side of my ODEs and plugging them into my explicit Euler equation. So let's say we wanted to take one step. Well, if f of n is equal to 0 at first, g of n would be equal to 1 coming from this, our initial condition, and h of n is equal to 0 coming from this initial condition. Then we could say, okay, well, f of n plus 1 then is equal to 0 plus, maybe we'll take a step of a quarter, 1/4 times our g of n value, which we get from here. So that's times 1, so that will be equal to just a quarter. Our g of n plus 1 value is equal to our initial value, 1 plus a quarter, times our h of n value, which is 0. So that's going to remain 1. And then our h of n plus 1 value would be our initial value, 0, plus our time step, 1/4, times minus 1/2 times g of n, which is initially 1, times f of n, which is initially 0. So this remains 0. And so these would be the values we would have at t equals to a quarter. Once we've completed the full step, we could then use those values to determine the next step. Okay.